Hello, in this session we will discuss about Heisenberg's uncertainty principle. This principle quantifies the uncertainty associated with non-commuting operators. In our previous sessions we have discussed what is all about non-commuting operators. Two such non-commuting operators that are used frequently in quantum mechanics are position and momentum, and time and total energy. This Hamiltonian operator corresponds to total energy. So Hamilton total energy operator and time operator, they are non-commuting operators. Similarly, position and momentum operators are non-commuting operators. If this commuting operation gives the result 0, then those operators are called as commuting. If the result of commuting operation gives a result that is equal to not equal to 0, then such kind of operators are called non-commuting operators, and Heisenberg's uncertainty principle is applicable to non-commuting operators. So we'll be mostly confine ourselves to position and momentum only. So Heisenberg quantified the uncertainty associated with non-commuting operators. So he quantified the uncertainty associated with position and uncertainty associated with momentum. So uncertainty associated with momentum is delta p, and uncertainty associated with position is delta x, and he quantified this value, this product of two uncertainty, which is greater than or equal to h bar over 2. Now this derivation of this equation 1, or this quantified value or quantified expression, will not go into the derivation of this how this value is obtained. We'll directly use this value because the entire derivation is out of the scope of this syllabus. So we'll take this quantified expression as such, and we'll do our mathematical expressions with relating to position and momentum of the quantum mechanical system. The equation 1 can also be represented as the inequality of equation 1 can also be represented as standard deviation. Means standard deviation with respect to position momentum, that is sigma p, and standard deviation with respect to position, that is sigma x. What are standard deviation? If we do a large number of experiments or large number of eigenvalues if we obtain, then the distribution of large number of measured values of position and momentum is called the standard deviation. Similarly, the standard deviation with respect to position and the standard deviation with respect to momentum, and their product is greater than equal to h bar over 2. This is also Heisenberg's uncertainty principle. Now, how the standard deviations are represented? The standard and the variance with respect to momentum is expectation value of p square, that is expectation value of momentum square minus expectation value of momentum taken to the power square. Similarly, the variance associated with position is equal to expectation value of position square minus expectation value of position taken to the power square. So if you do that, we get the variance with respect to position and variance with respect to momentum. Now to get the standard deviation, we take root over of these quantities, and we can get the standard deviation with respect to momentum and standard deviation with respect to position. So to justify Heisenberg's uncertainty principle for any quantum mechanical system that we have studied or we will study, we have to first find out the variance. Then from those variance we can find out the standard deviations, and from those the product of standard deviations we can verify whether that system is following the Heisenberg's uncertainty principle for two different operators or not. We can verify in the above stated way. So how to get the expectation values? From fourth postulate of quantum mechanics, we have observed that if the wave function or Eigen's function is normalized, then the expectation value is given as integration taken over whole space, then the complex conjugate of the eigenstate, then the corresponding operator. Here the operator is p square. We are taking expectation value of p square or momentum square. So I have to write the operator for momentum square. Then the eigenfunction is such, first complex conjugate of eigenfunction, then the operator and the eigenfunction, and integration over whole space. If the function is not normalized, then I have to divide through a normalizing condition, but we are assuming that our wave functions are normalized, so we are ignoring those normalizing conditions. So this is how we obtain the expectation value for momentum square, momentum, position square, and position. Now we'll apply this knowledge to, we have discussed one quantum mechanical system, that is one particle in one dimensional box and we extended that knowledge to particle in 3-dimensional box. So we'll verify whether position and momentum operators are following Heisenberg's uncertainty principle for particle in one-dimensional box. So for particle in one-dimensional box, the normalized wave functions are given by root over of 2 over a sine n pi x over a. What is a? A is the length of the box, total length of the box, and x is the length variable, the distance variable. So, and n is the quantum number. N is the quantum number, and n values varies from 1 to 3 like that. So this one we have discussed in one-dimensional box. Now we will study whether the position and momentum operators are following Heisenberg's uncertainty principle or not. So the momentum operator is minus I h bar d over dx. Now before verifying, we'll use two standard mathematical integrations, standard mathematical integrals in our verification. Those integrals are x sine square bx dx is equal to x square over 4 minus 1 over 4b x sine 2bx minus 1 over 8b square cos 2bx. Similarly, the other standard integral that we will be using is integration x square sine square bx dx is equal to this quantity. So we will be using these two standard mathematical integrals to verify whether position and momentums are obeying the uncertainty principle for particle in one-dimensional box. Now we have to take expectation value of x, that is the position. So integration, the limits are 0 to a, length box length is a, I said. Then the wave function, the operator, the position operator is x, we have to multiply simply by x. Then another the same eigenfunction, this is a real eigenfunction. So there is the complex part and the real part are same. So we have to take, if we multiply that, the constant term 2 over a will come out of the integration, will be left with x sine square. If I consider this quantity as theta, then I can apply this standard mathematical integral. Here I am missing a dx term. Then I can use this standard mathematical integration and I get the value a over 2. Similarly, for expectation value for position square can be found out as aq 1 over 3 minus 1 over 2 pi square n square. The expectation value for momentum is 0. This one we have already discussed. The expectation value for position and momentum we have already discussed in our one-dimensional box. So there also we have discussed that expectation value of momentum is 0 and expectation value for momentum square is n square pi square h square s bar square over a square. Now we have to find out the variance with respect to momentum and variance with respect to position, or the standard deviation we have to find out. Variation means square, but we'll find out the standard deviation, so we have to take root over. So standard deviation with respect to momentum is expectation value of momentum square minus expectation value of momentum taken to the power square. So expectation value of momentum taken to the power square is 0. So I am left with only the expectation value of momentum square, and that comes out to be n square pi square h bar square over a square, and if I take root over, I'll be getting n pi h bar over a. This is the standard deviation with respect to momentum. Then standard deviation with respect to position, if I do the same thing, the position square, the expectation value of position square minus expectation value of position taken to the power square. If I do the mathematics, I'll be getting a root over of 1 over 12 minus 1 over 2 pi square n square. Now I've got my standard deviation with respect to position and standard deviation with respect to momentum. I'll multiply those two quantities and I'll see the value. The mathematical value that comes out to be is 0.57 h bar. Now this value is essentially greater than h bar over 2. So our Heisenberg's uncertainty principle says the product of standard deviation with respect to position and standard deviation with respect to momentum should be greater than equal to h bar over 2. In our case, we are getting a value 0.57 h bar, and which is greater than h bar over 2. So for our system, that is one-dimensional box system, the position and momentum operator are following the Heisenberg's uncertainty principle. We will apply this uncertainty principle to other quantum mechanical systems. We will be discussing the simple harmonic oscillator problem. There also we will verify that the position and momentum are following the uncertainty principle. So with this, I'll stop here. Next session we will discuss about classical harmonic oscillator. Thank you.